So this is part 3 of Introduction to Thermodynamics. And on the last video, we looked at the formula Q equals mc delta T. And this is more often referred to as Q equals mcat. Now, Q stands for the heat that's either gained or lost. M is the mass of the substance. C is your specific heat capacity. And it is a constant. You would actually make sure that the specific heat that you plug in matches the substance that you plugged it in for. So every substance has a specific predetermined specific heat capacity. So you have to make sure that the C that you plug in is for the same substance that the mass is for. So like if you plug in the mass of water, you're going to plug in the specific heat of water. Now delta T stands for the change in temperature, and you calculate delta T by taking your final temperature and subtracting your initial temperature from it. So you have to read for context clues. Sometimes you rearrange this formula to solve for C. So if you were to rearrange that, you would get C is equal to Q, the heat, divided by the mass of the substance times the change in temperature. This is just reiterating what I just went over. Now we will do calculations involving Q equals mcat after when you get back to class. I do want to scoot back just a second and just talk about here. Notice this table before. It's giving you water, liquid water, ethanol, solid water, vapor, water vapor, solid aluminum, solid carbon in the form of graphite, iron, copper, mercury, lead, and gold. But notice they all have different specific heats. I also want to point out that the units for specific heat are joule per gram degree. So it could be joule per gram Kelvin. And since 1 Kelvin degree change is equivalent to 1 degree Celsius change, it is acceptable to interchange these as joule per gram degree Celsius. So these are interchangeable. So this will be the same for joule per gram Celsius or joule per gram Kelvin, because for 1 degree in the Kelvin scale you change. Remember, you're changing by 1 degree on the Celsius scale. The next thing we want to look at is a law known as Hess's Law. And Hess's Law can be applied to state functions, as I mentioned earlier. Remember, state functions are functions that are independent of the pathway taken. Again, I'll go back. I was talking about like if we were to be on top of the mountain, it doesn't matter how I got there. There may be 10 different ways to get there. I can hike up from the bottom. I could ride a bike. I could drive a vehicle. I could parachute from a plane. What matters is the position I'm at that moment. So Hess's law can be applied to state functions. And what it says is, in going from a particular set of reactants to a particular set of products, the change in enthalpy is the same, whether the reaction takes place in one step or a series of steps. And we actually looked at Hess's law back in the kinetics chapter when we were looking at our elementary steps and adding them together to get our overall chemical reaction. Now this is Hess's law shown in a graph form. Again, looking at your energy diagram, this red line here represents the energy of your reactants. The red line down here represents the energy of your products. So basically, between the reactant and products, when we define the overall delta E, which we also call delta H, the enthalpy change. And by the way, would this be endothermic or exothermic? Look at where your reactants are, look at where your products are. So this will be exothermic, very good. So that means it would have a negative sign, okay? But anyway, it doesn't matter if I go straight down, okay? Or if I go in multi-steps, like 1 step, 2 step, 3 step, 4 step. What matters is that I end up at the bottom on this particular location. The energy change, the delta E, is the same between the reactants and the product. So this is a state function. So let's look at an example of Hess's law problem. So this says calculate the change in enthalpy for the combustion of methane. So if you're given a couple of elementary steps, like here's 3 of them, you got to figure out how to get them to add together to give you this overall chemical equation, okay? So you might have to flip a reaction around. Now, if you do have to flip a reaction around, what would happen is you would change the sign of your delta H for that reaction, because if it's endothermic in one direction, it's exothermic in the other. So if you flip it around, you have to change the sign of your delta H. Also, you might have to multiply through to get your coefficients to match up with the coefficients we see here in this balanced equation. And if you multiply your little elementary step, you're going to have to multiply your delta H value as well. So let's look at how we would do that. Here's our elementary steps again. First thing I have to do here is I notice that I need methane to appear as a reactant. So I've got to do something with this one. I've got to take this and flip it around. So I'm going to flip this around, and when I flip this, we reverse the reaction, so we got to reverse the sign of delta H. Now the step 2, keep that reaction number 2 unchanged because the CO2 belongs in the product side. So since I see the carbon dioxide in the product side here, if I leave it like it is, it's going to stay in the product side there. Again, we talked about the methane, so we flip this one, and so I'm going to change the sign of this. And we're going to leave this one as is. So we're going to leave this sign the same. Now for reaction 3, I've got to multiply it by 2 in order to get my coefficients to be correct. Because notice I have 2 waters here and only 1 water here. So if I multiply this by 2, then I got to multiply this by 2 as well, that quantity. After you've done that, and we'll look at the next slide here how that happens. So here's where I did those changes. I flipped that around, so I changed my sign to positive. For the next reaction, I left it the same, so I leave this the same. Take the third step, I multiplied through by 2. Multiplying through by 2 made 2 here, 1 here, and 2 here. So I had to multiply this value here also by 2, because if I multiply here, I got to multiply here. If I divided here, I'd have to divide here. So now, once you've done that, look at what happens to the intermediates. The carbon here cancels with the carbon. Your 2 hydrogens cancel out. And if you look at what's left over, you have CH4, and I had CH4 here. Notice I have 2 oxygens total, and they're on the same side, so I add them. So 2 oxygens here. And I have 1 carbon dioxide and 2 waters. 1 carbon dioxide and 2 waters. So I can add these together, and that gives me the balanced equation. They match. And so all I do now is add my delta H's together here, and that's going to give me overall a negative 890.36 kilojoules. So this will be an exothermic process because of the negative sign there. Another way that we can calculate the heat of reaction is by using what I call this the summation formula. The change in enthalpy of the reaction, or XN stands for reaction, is we could use the formula where you sum up the delta H, the heat of formation of your products. You would add all that up and then subtract from that where you summed up the heat of formation of the reactants. Now these values here are in the appendix of your book, but I've brought them over to on this slide. These are the values for the heats of reaction for each of those substances. So if you plug those numbers in, again, the products first, so you do these 2 first, and you got to take into account the coefficient. There's a 1 here, 1 mole here, 2 moles here of the water, 1 mole here, 2 moles here of the oxygen. When you plug those in and add it all together, you get negative 890.36 kilojoules. Same number that we got on the previous problem, but this is a second way of calculating it using this formula. Again, I call this the summation formula. And we will work through some more. I would pause the video here and go back and try to work this out if I were you, and then just make sure, verify that you get the same numbers I get here. But this number, same number, is exothermic. We used Hess's Law in the last example. Here we're using the summation formula. Okay, that's all for this video.